Assalamualaikum warahmatullahi wabarakatuh and welcome back and good morning, good afternoon already. So sound check. So please someone.
Yes, sir. Exactly, sir.
Yes,
Okay,
doctor.
okay, good. Thank you. So it's getting raining here. So my room is getting darker. Okay, so this is we are still in LTI system function topic, and this is a part 2. Okay, so we have seen what is a system function. System function is denoted as a HZ. Right? So what is a HZ? HZ is a Z transform of an impulse response. So this is actually we have seen that. So we are giving it a name. Okay, so today, so we know that it has a name. So it's very important. It has a name. So we call it a system function, which is a HZ. And so we have seen one application why we need this system function, because it has the relationship of yz over xz. Okay, so this is the one that we already know now, and we can do this to do an inverse z transform to get a difference equation. So because of this, so we can do a conversion between impulse response and difference equation. Okay, so from time domain, impulse response is a time domain, and then we go into a different domain, which is z domain, do something in z domain, and then return back to time domain, which is a difference equation. Okay, so to convert between impulse response to difference equation, which is both are actually time domain, so we need to go partially into a z domain, right? Before we can convert it. Because as I mentioned that doing everything on a time domain is not as straightforward. It's not straightforward. Okay, so we need to convert it into a different domain so that the maths becomes easier and simpler. Okay, now we're going to look at this thing because I've been talking about system realization even from the beginning of the first session today. Okay, what is a realization is implementation. It is implementation. So our final product. So how our final product should looks like. Okay, so how do we optimize it? And we have seen one simple optimization here from when you have impulse response of Hn, those things, we have 10 samples for Hn. This is, even though this is a FIR, and we can convert this into from this very long equation, so which use a 10 memory and then 9 summation, and if we have a multiplier here, so we are actually having a 10 multiplier. Okay, a lot. And we can simplify that. We have seen that into this a simpler or a shorter version of the system. So instead of a 9 summation, so now we have only 2 summation. So this is plus 1, this is plus minus 1. And we just need a 1, 2, 3 memory location. So to do this, so one is for xn, another one is for xn minus 10, and then this is yn minus 1. Okay, so we just need to keep these 3 values to do it. So the rest, we doesn't need to keep it. We doesn't need to store it in our RAM because this is not a permanent values. Okay, this is a temporary. So after we reset or we shut down the system, so everything will be gone. Okay. Except the multiplier, this is 1, this is minus 1, this is 1. So these are the things that we store in our ROM. When you run the system, so it will call this value, this 1, minus 1, and 1 from your ROM. Okay, it will call it from your ROM. Okay, and we will see a more realization of how we do how there's a standard way of how we can optimize it. Okay, so we're going to look at it in this second session. So after a filter is designed, it must be realized by developing a signal flow diagram. So we use this one, the signal flow diagram, so that the design is a bit clear. So it's like if you want to do a programming, so you should have a flow process. Okay, so you should have that one. So, but this one, if you are designing a filter, so on a digital system, so we do flow diagram. So we do flow diagram. Okay, because that one is it's like some visualized thing, so that we can understand the system better. Okay, rather than just doing the coding, so it's just lines of codes. Maybe just it's not easy to visualize. Okay. A given transfer function may be realized in many ways. Consider how a simple expression such as ax plus bx plus c could be evaluated. One could also compute the equivalent, this equation. We can also write it as x a plus b plus c. And this one, so we have 1, 2 multiply, 1, 2 summation. But this one we have 2 summation and 1 multiplication. Okay, so what is the difference? So this is 1 multiplication, so this is a 2 multiplication. And I think everybody already understand that doing multiplication is actually a complex process. Okay, so you have done that in your, I think, digital system. How do you design a multiplier for a processor? Okay, so there's a lot of things. Everything starts with summation. Okay, and then from a summation adder. Okay, so I think digital system or electronic digits, so you have learned about adder. And then from adder, you design a multiplier. So multiplier is a lot. So this is like a very simple example that if we can reduce the multiplication process, actually we are optimizing our system. We are optimizing our system. Right? So here the discussion will be on computing the implementation cost of several implementation methods based on number of addition, multiplication, and memory location. So we have seen that in our last example from 10 memory location that you need. So we can optimize it so that we use only three memory location. Okay, so we optimize it that way. And to do that, so it is easier that we have this one as we have read here, a signal flow diagram. And to do that, so we have several symbols. So this is addition. So we have this one, that circle with plus. Everybody already familiarized with this thing. And then this is multiplication. Multiplication is just an arrow. So you have one arrow, and then the multiplier. Okay, arrow, multiplier. So if we have xn here as an input, and then it found this arrow with a multiplier value. So this is where we have that axn. Right, and then this is delay. We already know that when we learn Z transform, inverse Z transform. So a delay by one sample. So Z to the power of -1 is actually delay by one sample. Right, so this is actually delay one sample. So we're going to use this one. So we're not going to have a Z to the power of -2. So we're not going to have that. So if we have two delay, Z to the power of -1 and Z to the power of -2, so we're going to have to use a two block. We need 2 blocks, right? So that we know that. So if we have a Z to the power of -2, so we need 2 memory location. Okay, so that's the things. So that's why if you have xn delay, then you have a xn -1. And this is a block diagram. It's just a term. When you use block diagram, everything is in block, in circle, those things. But signal flow graph, this circle becomes just a dot. And a delay is just there's a no block. You just put it as a Z -1. So it's like an arrow. You have a Z -1. But this one is an arrow with a multiplier value. Okay, a weight. We call it a weight. That multiplier is a weight. Okay, so that's the symbol are very easy because why we have only 3? Because LTI system only involve 3 operations: addition, multiplication, delay. So it doesn't have any others, right? Only these 3. So that's why the symbol is only 3. And a lot of equation here. So in general, system function of a system is represented by, we already know this, yz over xz, which is equals to hz. So we have numerator and this is a denominator. Okay. Okay, we skip this, a lot of equation there. So we want to make everything simple. So this is the first one. We call it direct form structure for FIR. So how can we design a system so that we're going to put it on this form, this structure. Okay, so what is a structure? Structure is, if we look from our last example, so we can say that this is one structure, a very simpler, a shorter structure. This is another structure. Okay, this is one form or a structure, and this is another form or another structure. Okay, but what we're going to learn here is this is a standard and generalized structure. So we call it direct form structure for FIR because we have two types of impulse response or system. What is an impulse response? Impulse response is representing a system. So that's why sometimes we call it. So we have two types of system. So we can say that we can say that two types of system or two types of impulse response. It is the same meaning because impulse response is representing system. So this is one type of system, FIR. We have another one, which is IIR. For FIR, so we're going to look at two structures. So this is one, direct form. The other one is a direct form structure, a linear phase. Or we can call it a linear phase direct form structure. Okay, so what is a linear phase? We're going to look into this, what is a linear phase, in detail later. Right? But for now, so we just need to know that. So there is an FIR system which we call linear phase. We're going to look at how does it look like. So this is very important because whenever we design a system for FIR, as much as possible, we want to make sure that it is linear phase. So that's the reason why. And we're going to look into detail for this later. Not today, not this week. Okay, so two types of a structure for FIR. So let's see the first structure. The first structure is actually very direct. Even the name is a direct form. So what we do is, so this is actually what you do. So this is the xn, and then you have your multiplier here for the first samples of the first value of your impulse response. So this is the second value of your impulse response, the third value, and until the last value. Okay, so this is the last value. So what we have here is this is xn multiplied by hn, get 1. So this is h0 multiplied by xn. Right, so this is delay by 1. Delay by 1, so then you will get h1 xn minus 1. Okay, because we have h1 here. And then this is a h2. Delay by 1, delay another 1. So you have 2 delay. So this is h2 multiplied by xn minus 2. And so on. Okay, and so on. So, and then what is this? So this is plus because we need to plus everything. This one, this one, this one, and then the rest plus so that we can get the yn. Okay. And sometimes this structure is also, let's see one example. You can also draw it such this. Let's say we have xn, let's say 2xn plus 3xn minus 1 minus 3xn minus 2. So actually you start with xn, and then you should get your yn, and then you need to sum everything. So if you go to yn here, for xn, you need to multiply by 2. So actually you have 2 here. Xn multiplied by 2, so 2xn. So that is only 1. So we need to sum. We should sum with the rest. And this is for the second term. What is the second term? You need to delay it by 1. This one? Delay by 1. Delay by 1. Delay by 1 and multiply by 3. Delay another 1. And then you need to multiply by -3. Okay, so this is xn goes here, it goes here, xn minus 1, this is, and then goes here, another z, so you have a xn minus 2, multiply, and then everything, all this, we need to sum. And we can do that by doing this symbol. So plus, plus, okay? So either you draw it such this, or you draw it such this. So doesn't matter, both are the same. Okay, so this is what we call a direct form structure. So whatever you have, you just put it there and then do the plus. So we can see everything, all the value, all the delay directly. So that's why we call it direct form. Okay, so then from here, we can see that's very clear. How many summations? So 1, 2 summation. How many memory that you need? So this is 1, 2. And then of course you need to have an xn, so 1, 2, 3. Okay, so how many multiplication? 1, 2, 3 multiplication. So we can see it from here. And of course we can see it here also, because that's why we call it direct form. So next, we're going to look at not so direct, because we change that one so that we can have a less multiplication or summation or maybe a memory. Okay, so we try to reduce these three, either the summation, the multiplication, or the memory location. Okay, but for this one, it's not any FIR system, so it's supposed to be specific to what we call a FIR linear phase. So a linear phase FIR system. So what is a linear phase FIR system? It has a very specific form. So this is supposed to be the linear phase. Hn equals to hm minus n, or it is minus hm minus n. And for this one above, so we have two types, type 1 and type 2. And the other one, so we have a type 3 and type 4. Okay, so what is this? So actually it is a symmetry impulse response. When you have a symmetry impulse response, so we call it a linear phase, right? Type 1. Let's see, I think we have hopefully I have a slide from previous. This is inverse, this is Z transform.
There's a mention in this
yes.
FIR.
Pardon?
FIR.
Again?
There's a mention in this in FIR slide. An LTI system.
Yes. I think in this chapter. Let's
FIR, if I'm not mistaken.
Yeah, you might be correct. Okay, this one. Special FIR system. Last time, if you remember, we skipped this. We skipped this one. Okay, so now we're going to look at it. So because this is very special, and this is actually our target. This is our target, to have this kind of FIR system. So this is a type 1, type 2, type 3, and type 4. Type 1 and type 2 is actually what we call a symmetry. This one is an anti-symmetry. So symmetry where? So this is a symmetry at sample number 2. And how many samples? 1, 2, 3, 4, 5. This is odd number of samples. We can have a symmetry also with even number of samples. So this is an example of even number of samples. So we have 1, 2, 3, 4. So where is the symmetricity? Between 1 and 2. So it doesn't have a center. So we don't have this one. We have a center value. So but both are actually asymmetric. Both are symmetric, and we can represent that using this equation. Type 1 Hn is actually equals to Hm minus n. Okay, so for example, let me write that again. Hn is equals to Hm minus n. Hm minus n. So what does that mean? H0 is actually equals to H. What is the M? M is the highest index, which is 4. So, okay, so 4 minus 0, which is equals to H4. So what does it mean? So this one and this one is similar. And this one and this one is similar. Because this doesn't have a pair, this is at center. So then we can say that, okay, this is a symmetry. The same thing goes to here. H0 is equals to H3. H1 is actually equals to H2. Okay, symmetry. Type 3 and type 4. This is actually also symmetry, but this is we doesn't call it symmetry. Instead, we call it anti-symmetry because the signs change. If this is let's say this is 2, this one is minus 2. Okay, the value is the same, but the sign is different. Okay, either way. So let's say this is 1, this is minus 1. Same thing here. This is the odd number of samples. This is the even number of samples. And also, of course, we can have also something like this one start with negative. Let's say negative 1. And then this is 1. And then this is negative 1. 1. Okay, so this is actually type 4. This one and this one is the same, but on a different sign. This one and this one is the same, but on a different sign. Okay, to make it clearer, so let's say this is 2. This is negative 2. Okay, it just need to be a different sign. It doesn't need to be starting with a positive and then later it's a negative. So it just need to be with a different sign. Okay, so let's get back to this thing. We already know this. So this is Hn m minus n is for type 1 and type 3. And this is for type 3 and type 4. Okay, so what is the main features here is when you have a linear phase. So actually our Hn is symmetry or anti-symmetry. Okay, so that's the key. The number of multiplication is reduced to m over 2 for m even, if you have a m even, and to m minus 1 over 2 for m odd. So what is the m again? M is the highest index that you have in your impulse response. Okay, so this is the one that we can reduce. We can reduce number of multiplication. The number of addition and memory needed are similar. These things similar, so we reduce that. Right, so that's why this is quite important, because normally for FIR filter, for FIR system, so number of the length of the Hn can be maybe up to 100, 200. So that's a lot. So if it is a 200 length, So you divide it by 2. So you only have half, which is 100. So 100 compared to 200 is a lot of reduction. Okay, so we're not talking about 4 reduced to 2. It's not even 10 reduced to 5. So this is maybe above 100, and then you divide by 2. So that's a lot of improvement, a lot of a reduction. And actually, this is the general form, quite messy. It looks quite messy here. So, but let's do one example on how can we draw this. Okay, we can draw this, or we can draw on a different style. Let's say we have a yn equals to, let's say 2xn plus 3xn minus 1, and then plus 2xn minus 2. So which type is this? So this is actually type 1. This is type 1. What is a type 1? Type 1 is you have an odd number of samples, odd length. So in our case, 3. Okay, so this is 3. So this is 3. If you sketch, this is actually at 0, it is 2. At 1, it is 3. And then again, it is 2. Okay, so that's your HN. So how do we know this is a 2, 3, 2? Because we already seen that this is difference equation, and it is FIR. So what is our HN? HN is the coefficient B. So what are the coefficient B? 2, 3, and 2. Okay, so directly we can know that from this difference equation, what is the HN? Because this is FIR, so we can do it straightforward. If it is IIR, we cannot do this. So we need to do the Z transform. Okay, so that we can have the impulse response. Okay, so what we can do is we should have a XN. I need to put it a little bit lower. So let's say you have your XN. So this is XN, and that XN needs to be multiplied by 2. Okay, wait, I need to solve that one first. So actually, how do we reduce that number? Is because this is a symmetry. So what we can do is we can rearrange that into 2 multiplied by xn plus xn minus 2 plus 3xn minus 1. Okay, instead of 1, 2, 3 multiplication, now we have 1, 2 multiplication. Summation 2, so still 2. Number of memory, so this is 1, 2, 3, so we still have a 1, 2, 3. So because we are just reducing the number of multiplication here. Right? So now we're going to, if you draw this straight, so directly, so you get a direct form. Because this is a linear phase, it is a symmetry, so we have an option so that we draw our system as a linear phase. So we do this, 2 multiply by summing these 2 first. All right, so actually it's quite not that complicated. So you have your xn. You need to multiply by 2 later. Because we want to do this first, xn plus xn minus 2. So because we do the summation first and then multiply. So we do the sum. Actually, what we can do is do something like this. And we need to bring this so that it goes to here 2 times. Okay, this is 1 time. So we need another one. Okay, 1. So you get xn minus 1. 2, you get xn minus 2. and then this is xn minus 2 plus with your xn. So this is xn. So these 2 plus, and then multiply by 2. Multiply by 2. There you go. So multiply by 2. Okay, sum first and then multiply by 2. And we have another one which is 3xn minus 1. So it is xn minus 1. It is here. So we have it here. And that one needs to be multiplied by 3. Okay. And then what will be next? Sum. Sum both. So you get your yn. Okay. So actually plus first and then do multiply. So this is there's a no plus here. So just a 1, and then you can do that. Okay, let's see one more example. So that's you can see. I'm going to do a longer example. So this is like xn plus 2xn minus 1 plus let's say 3 xn minus 2, and then plus 3xn minus 2 plus 2xn minus 3. 1, 2, 3, 4, 5. Okay, another one. Xn minus 4. Okay, so actually this is type 2 because we have a 1, 2, 3, 4, 5, 6 number of samples. If we take the Hn is actually equals to 1, 2, 3, 3, 2, 1. Okay, so this is our Hn, the impulse response. So this is similar. This is similar. This is similar. So then this is symmetry. And number of samples is number of values is actually 6, which is even. So this is type 2. Sorry, this is type 3. Let's see. Type 1, type 2, type 2. Okay, type 2. All right, so we can draw this same thing. So just put your xn first, and then we rearrange that. Yn is actually equals to xn plus xn minus 4, and then plus 2 multiply with xn minus 1 plus this one, xn minus 3. And then the other pair is 3, xn minus 2 plus xn minus, this is 1, 2, 3, 4, 5. Okay, I'm making some mistake here. This is supposed to be 5. This is supposed to be 4, and this is minus 3. Okay, so we have a 3 pair because we have a 6 number of samples. So we group because it is a symmetry. So we have a 3 pair here. You all need to get used with my handwriting because that handwriting is not that good. So okay, xn do summation with something. We need to do that. Xn minus 5. So before we can get into this one, this is here xn minus 5. So you need to have 5 of this. 5 of this block. And of course, that 5 of that block can be 1, and then 2, And then it can goes to here 3, 4, and then 5. Okay, 1, 2, 3, 4, 5. So we can do this. And this is actually xn minus 1. So which is this one is xn minus 1 and xn minus 4. So this is xn minus 4. Similarly, this is xn minus 2. So it is paired with xn minus 3. So which is this is actually xn minus 2. And then you pair it with xn minus 1, minus 3. Okay, so this is going something like this. 1, 2, 3, 4, 5. So you get 5 here. 1, 2, 3, 4. You get 4 here. Okay, then so we have 3 summations. So we have 1, 2, 3, 4, 5 memory location, but the multiplication. So now we have only 3 multiplication instead of 6. So the first one is multiplied by 1. The second one, this is multiplied by 2. And the third one is multiplied by 3. Okay, 1, 2, 3. So 1, 2, 3. And we sum everything. You get your yn. All right, so why would we do why we do this? Just because so that we can visualize our system, so that it clearly shows that. So we have those how many numbers of summation, how many numbers of multiplication, and the memory location. Okay, so because of course, if you write a coding to your microprocessor, maybe this is not that critical. But if you go for design it on a gate level, right? So maybe this is very important. This is very important because you need to rearrange your gate, So you need this thing. So now it's 12:44. Okay. So any questions so far?
Doctor, the blocks for the delay, right? Do we have to write arrows or can we just leave it like a line like that?
This one, yes, actually you need arrow, but if you leave it without an arrow, it's not really a very critical error. But of course, to make it perfect, you should have an arrow. Okay, because everything needs an arrow so that we know that it goes to where. Because even actually this is not critical because we have only one direction. So everything goes to that direction. Okay. So, but later we will see when we go to IIR, so we have 2 directions. So we have forward and inverse direction. Then the arrow becomes very, very important.
Wow.
Okay.
Okay.
So on FIR, maybe it's not that critical because it is known. So, but of course, to make it, make sure you put an arrow so that everything becomes a good draw. Okay, this is next. So this is because we already know that FIR. So we have 2 structure. Okay, so one is a general structure, which is a direct structure, we call it. And second one is if we have a special FIR, which is a linear phase FIR. So what is the linear phase FIR? The impulse response is either symmetry or anti-symmetry. Okay, so if it is if the Hn is a symmetry or anti-symmetry, we call it linear phase. Why we call it linear phase? We will discuss that later. Okay, so we will have one chapter just to discuss on that one. So, and now for IIR, actually there's a direct form 1 and direct form 2. And in this slide, so we have a transpose direct form 2. So we have 3 structure. But we're going to cover only 2, which is the direct form 1 and direct form 2. So the transpose, I'm just going to just show you how does just a brief explanation on it, okay, so that you get the idea. So for the direct form 1, so this is actually the structure. So previously we have seen this thing. When we have FIR, so actually we have this one, and we doesn't have this one. So it doesn't have this. So because IIR, so we also have a sequence of the output sequence. So we have output sequence. So that's why we have this one. And this arrow is going to that direction. This is a forward direction. And this is actually a reverse direction. Okay, so that's why in this case, the arrow is very, very important. Okay, so let's see number of operation and memory. So addition is m plus n. So because m is actually the highest index of the input sequence, and n is the highest index for the output sequence. And later, this thing actually this is called order of the system. Okay, what are these? So this is actually order of system. So we call it order. And I think you guys already heard about order before when you design a filter. So there's a first order filter, second order filter, third order, fourth order, those kind of things. But in this case, actually we are looking at the highest number of m. It is actually similar. It is similar. Okay. So multiplication is m plus n plus 1, and then memory units m plus n. Okay, so it depends on how many sequence that you have on the input and output. So let's see one example. So do we have example here? So okay, just let's say we have yn equals to xn plus 2xn minus 1 minus, let's say 2yn minus 1 plus 0.5 yn minus 2. So then we know that we have, so this is where you need to be very careful. So there is a minus here. So this is minus A1. For B, there is no minus. So where does this minus comes from? Because of from the left side, so we change it into the right side. So the sign actually changed. This is actually yn originally plus 2 yn minus 1 minus 0.5 yn minus 2, which is equals to xn plus 2xn minus 1. Okay, so what is A? What is A? A is actually equals to 1, 2 minus 0.5. What is B? B is 1, 2. Okay, so this is A, this is B. So, but in our equation, this is what we call one that I said that typically we write our equation such this, and this structure is actually following this. So you need to have your minus here, because what is the add output? Output is yn. The output is not this thing, so it is yn. What is the yn? All these two terms you need to bring it to the right side of the equation. So that's why the sign change. Okay, so need to remember that this one no minus, so you have minus here. So because this is just a direct form, so quite easy to do it. And this B is not your Hn. Okay, this is not equal to Hn, because now this is IIR. If this is FIR, yes, B is equals to Hn. But in this case, no. So this is not Hn. So be careful on that one. Then we just write our, we can draw it straightforward. So we have xn, so we have yn, and then xn, so we have just 1 and 2. So this is, we call a B1. So this is this is B0. This is B1. B0, B1. We doesn't need to put A0 because A0 is always 1. Okay, we have B0 because it can change, so you can have any value. But yn, we doesn't have to put it here because it's always equals to 1. Okay, so if you want to have the that yn, so this is actually somewhere equals to 1, always. All right, so let's draw that. So this is xn. So xn is, it's going somewhere here, and then you have a delay of 1. So we have only 1 here. Z minus 1, put an arrow. This is where you need to sum. This is 1, and then this is 2. Oh, sorry, not 1, this is 2. 1, if you want to put a value 1, it's okay. If you leave it, it's okay. Okay, either way, it's okay. And then this is yn. So if we look at this diagram, so now you need to do a reverse arrow and a plus here. So you have a plus, make it a little big so that it goes to y. And then, so you have z minus 1, but you have a 1. This is 1 delay. So this is 2 delay. Another one, z minus 1. So this one goes to here. Okay, so now we have 2 parts, and yn, so this is always 1, z minus 1, so this is supposed to be minus of this one. So this is actually minus 2. And then this is 0.5. Right? Or if we are looking at this form of our equation, difference equation, so we can say that this is minus 2, this is 0.5. Okay, minus 2, 0.5. And then just connect both so that you have a complete system, this one. Okay, so this is a direct form. So whenever you have this equation, you just do on the input sequence and then do on output sequence and then connect this arrow so that we have all summation for y. Okay, this is quite easy. And for direct form 2, we have an equation here. So this is how it is actually derived. But after that, so we have a general form. So this is general form. So instead of a separate, it's like if we look at here, so we have a separate block for input sequence. This is another block for output sequence. And we have a 1, 2, 3, 4, 5. We have sum here. So we have sum operation here. So what does it do in a direct form 2? This z minus 1. Now the plus is at this section. Now the memory is actually reduced. Okay, memory is reduced. Instead of having this part of memory for input sequence and this part of memory for output sequence, so we can combine these two. And it put it such this. Okay, so this is then we reduce the memory into half. Okay, you just need to draw it this as this form. So if we go back to our example, so let's go back. So the A is, try to memorize this. A is equals to 1 to 0.5 and then 1 to. A is equals to 1 to 0.5. Hopefully I'm not mistaken on the negative. Okay. And then B is equals to 1 and 2. Then, because you know what is the A and B, so you just plug in all the values inside the diagram. So xn, and then you should C plus first, and then yn. So you should see again the plus first. Okay, so that plus and that plus, and then at the center, so we have the z minus 1, and then z minus 1 again. This is connected there, and then you should look at the arrow. So all the arrow is going up, and then the arrow going down on at the center. Okay, go down 1, z minus 1, go another 1 because the highest is z minus 2. Okay, so the highest is here, which is z minus 2 delay. All right, and then plug in everything else. So this is goes to here, plus, and then goes up, and then this is another plus, goes up, and then this is, if you want to put it there, so plus over there, and this part's supposed to be B, this part's supposed to be minus A. This is 1, and then this is 2, so, and then this is, it doesn't have this, so this is a 0, and then this is minus A, so which is minus 2, and then this is minus 0, sorry, not minus 0.5. So this is 0.5. Right? So you're done, because why this is a 0? Because actually at the back, this is 0. Because we are actually, it's like sharing the memory. So we need to push that one. We need to push that one. Okay. So either you multiply by 0, because in designing that, in writing a coding for this one, so actually you need to multiply with 0 here. Okay. So that's how you do it. For transport direct form 3, you see now, the summation is even reduced. So previously we reduced the number of memory. So now we reduce number of summation. Multiplication is still the same. Multiplication is still the same. Okay, we doesn't reduce number of multiplication, but we reduce number of summation and memory. Okay, so instead of writing it such this, so you're going to draw it such this. And to do this, of course, this is just a visualizing the system. When you want to do a coding, so you need to write this equation. Okay, so that is actually one skill that you need to have. You have an equation. How do you translate equation into coding? So hopefully you can do that. Okay. Okay, any questions? So we'll stop here. Any questions? So if there is no question, so again, we will have a test on this Thursday. So hopefully everybody get ready. And if just last reminder here. So during the test, the camera should be turned on using a second device or mirror setup. Okay, so everybody needs to have this. So if you don't do this, so I will need to make sure that you do that first, and then you can answer the questions. Okay, I think everybody already familiarized with this. This is not the first semester that we do this. So please make sure if you're going to use the second device, make sure your second device is ready. If you want to use mirror, so your mirror is ready, right? So, okay, so this is, make sure you have this. So if not, you'll not be allowed to take the test. Okay, so this is actually one of the requirement. Okay, so last call. Is there any questions? Last call. So by that, so good luck, everybody. Any question, please ask me, so we can discuss with me any questions. Okay. So anything that you don't understand, anything that's confuse you. So if you have any do some question and you cannot do it, so you can ask me. Right. So make sure you just do that in the preparation for the test. Okay. All right. So that's all for today. So see you guys again this Thursday for our test one. Assalamualaikum warahmatullahi wabarakatuh and good afternoon.
Waalaikumsalam. Thank you so much, Doctor.
Doctor, any final tips for our test?
Tips?
Yes.
The tips is actually the question is very easy.
Okay.
So please do the past year questions. You can get it from e-learning.
All right then.
Okay.
Okay.
And the best is actually try to do all the quizzes in the notes. Okay, so if you can do that, if you can do the previous questions, I think you will be good. I think you'll be good.
All right then.
All right. So you need to do it first, then you will know which part that you don't understand. If you don't understand, so you please ask me. All right. Okay.
Okay.
Thank you, Doctor.
Thank you, Doctor.